Hello everyone, my name is Bharat Dow. Let me just first check whether screen share is available. Share content screen. Yeah, okay. So hello everyone, my name is Bharat Dow and I'm a doctoral student at the Department of Chemical Engineering, IIT Kanpur, and I welcome to you all to this third lecture of tutorial session on NPTEL course of Advanced Thermodynamics. Okay, so we'll just wait for a couple of minutes to start. In the meantime, I will write the title of the talk. Okay. So, lecture 3. So, let us start. So in this class, we are going to study about the week 3 of the Advanced Thermodynamics course. So, and I'm going to solve some sample problems, which would help you in solving the assignment questions. Okay. So the first question for today is based on the Lagrangian multiplier. So let me just write down the question. Okay. So the question is question number 1. The dependent variable y dependent variable y can be written in terms of, oh sorry, the question, this is not the question. The first question is that let's say that you have a function which is, let's say, f of x is equals to y is equals to x plus 1 square. Now given that z is the intercept, the value of z in terms of x is, in terms of x is, so there are four options. So let me just write this down, then I will explain the what is asked. Okay. uh, so what the question is all about, so let me use a different pen, like this one. So what is given to us? We are given a function f of x, which is a function of a single variable x, and it is given by x plus 1 equal to x plus 1 whole square, y is equal to x plus 1 whole square. And what we are given is, we are given that z is the intercept. Okay. And what we are asked is, we are asked what is the value of z in terms of x. Right. So basically what is happening is, let's say this is some function. Let me use a different pen. Let's say solution. Here only let me draw. So let's say we have a function which is y is equals to f of x equals to x plus 1 whole square. Okay. So let's say we have an axis like this. Let's say this is an x-axis and this is a y-axis. And let's say this function is like this, some function. Let's say this is the function. Okay. Now this is f of x. Now what we are asked is, we have been given this value of this f of x, which is x plus 1 whole square. And let's say it is cutting the x-axis, y-axis at some point. Let's say this is point A. Now this is what is meant by intercept, right? So this is what is the meaning of intercept. And this is what has been asked here, right? So here, if you look at what is the value of intercept. All right. So I hope the question is clear to everyone. Okay. And that is one thing. And then the next point is, you are asked to find what is this value of this x, right? So in this, the concept which we are going to use is Lagrangian concept is uh, not Lagrangian, it's legendary transform. Legendary transform, right? The concept of legendary transform is what you are going to use. So I'll give you a couple of minutes to solve this question. Okay, and then I will solve it. Okay. So it's I'll give you 5 minutes to solve it. Okay. Yeah. Maybe I will also switch on my camera. Yeah. I hope you guys can see me. Yeah. So I'll give you 5 minutes to solve it. Remember, so one thing which has to be remembered here, this is the y-intercept, and how, if you remember what is the y-intercept, so let's say for example, if you have a straight line, y is equal to, let's say, mx plus c, right? So remember that this is the slope of the line, and this is the y-intercept, right? And what is this slope? This is the, if you remember, this is delta y by delta x, which is nothing but dy by dx. That is the derivative of x. And here you have already been given a function. So a hint would be take a derivative. Take dy by dx, that is d by dx of f of x. And the answer would somehow be related to this d by dx of f of x. Okay. So I'll give you 2 minutes to solve it. I think the question is clear to everyone, right? If the question is not clear, you can ask it. But I hope the question should be mostly be clear. So I'll give you a couple of minutes to solve the question. So has anybody been able to solve it? I hope the question is clear to everyone. So let me just give you one more hint. You'll again be using legendary transform. I think I have already told. But let me go ahead with the solution. Okay. Okay. The solution. Yeah. So what we are given is we are given y, which is an independent variable, which is a function of x, and this is 1x plus 1 whole square. Now what is this? This is an independent variable, right? Independent variable, and this is a x is dependent variable. Okay. So let me go to the next page. Okay. So what we are given the dependent variable. So we can clearly the dependent variable can be written in terms of x, right? Here you can see this is the independent variable and this is a dependent variable. So so the dependent variable y can be written in terms of the independent variable of x, right? So here it is of this form, y is equal to f of x, right? So this is so here what we are trying to do is this is an independent variable and this is a dependable variable. So we are trying to express independent variable in terms of dependent variable, right? And so slope will be what? Slope will be nothing but that at any point to this curve, we take a tangent, and that tangent when it the point at which it intersects the y-axis, that is nothing but going to be the y-intercept, right? And that is what we are asked to find, right? So so let me write this whatever I said. Let me write this down. So the dependent, sorry, the dependent, the dependent variable, which is nothing but y, right? can be can be written can be written in terms of independent independent variable independent variable x as following, right? Y is equals to f of x is equals to x plus 1 whole square, right? And the intercept, in this case the intercept, let's say, is given by z or denoted as z. Now in Legendre transform what we have, so here what we invoke what is Legendre transform, right? Invoking Legendre transform, invoking the concept of Legendre transform. So before that, I hope the concept of legendary transform is clear to everyone. So if not, so I will just give you the statement of legendary transform. So the statement. So what legendary transform basically tells. Let's say I have a function. Let's say, let me use a different pen for this. Now, what is legendary transform? What is legendary transform? Right. So legendary transform basically tells that let's say this f of x. This f of x contains, let's say it has some expression, right? So this so all the information which is present in this f of x, let's say if we have its functional form, then we know all the information about f of x. But now we want to express this safe information not by taking let's say we don't have an access to this f of x. We don't have direct access to f of x. So but we still need the information about f of x. So what legendary transform basically tells? Legendary transform basically tells that even if you don't have a direct access to f of x, you can still construct f of x from in an indirect manner if you are given some other information. Now, what is that some other information? That other information is nothing but the slope, that is the equation of the tangent drawn at a particular point. And if you have equation of all the tangents drawn at all the points, then in indirect manner we are able to find the we can find the function. So essentially all this all the information about the function can be known. So I will, before we start, I will just explain this. Right? So we go like this. Okay, like this. So let's say I have this function. Let's say some function f of x. Now let's say I don't have access of this function. I don't have the functional form of this thing. Okay. So now even if I don't have the functional form, I can still, let's say these are the for the simplicity, for understanding purposes, I will just discretize this function. Let's say these are the points which I have. Okay. The concept applies same for a continuous function. Now I don't have access to this f of x, right? But I have the access if I draw the tangent. Let's say this is the tangent one. Let's say this is tangent one. Then let me say this is tangent two drawn at this point. Okay, so this is point x1. This is point x2, right? Sorry, yeah, this is point x2. And this is point x2. Let's say this is point some. This is point. Let's say x3. Now I have information about the tangent line. For that tangent line, what I need? I need just the slope, right? Slope at this, which is nothing but dy by dx, and else what I need? I need this y-intercept. And if I have this basic information, then y is equal to mx plus c. So based on this expression, if I have that equation of tangent line for all of this, then I can still reconstruct this function, not directly but an indirect way. So all the information, whatever has been possessed by f of x, I can still have direct sorry, I can still have indirect access to it. Even if I don't know the functional form of, or I don't have the explicit access to this f of x, right? Explicit access to this f of x. So that is basically what is this legendary transform. So it transforms my f of x to some other g of x or g of some x dash, such that and this g dash x is what it is expressed in terms of this. These are nothing but the family of the tangent lines drawn at each point, and this family of lines are going to have two parameters, which are slope of the line and intercept. And that is why at a particular we are that is why in this question we are asked to find what is the value of that intercept. Similarly, a similar question can be constructed where you are asked to find the value of this slope, but for present case we'll limit ourselves to this value of this intercept, right? So I hope the this explanation is clear to everyone. So legendary transform is nothing but taking a function, and if we don't have and expressing that function in some another indirect way in terms of family of lines which are tangent to each and every point of this function, and then we express this function in terms of this family of lines, right? So we'll let us start. So I hope this concept is clear to everyone. Okay, so I'll give you a couple of minutes to write this down, and if you have any questions, you can ask me. I'll wait for a couple of minutes for you to ask the answer. Okay, if you don't have any answer, if I think nobody's answering, so I think that nobody has any doubts, and I will proceed further. So just to recap, so we have this function y is equal to f of x, and this is an independent variable, and x is a dependent variable. Okay, And what we are need to find is, we want to find, let's say z is the intercept. So then what we need to find is, we need to find this value of this intercept. Okay, let us proceed. So now let's go back to, so I have expressed what is Legendre transform, and we'll take use of this Legendre transform. Okay, so now in Legendre transform, so what we have now in Legendre transformation, old independent variable is replaced by the slope. Okay, and the new function is given in the form of, what is it? This is just the equation of line, which is, let's say z is equal to y minus kx, right? So let me write this down. So Legendre transformation, Legendre transformation, old independent variable is replaced by the slope, right? I hope this is clear to everyone. Okay? So what we are trying to do is, we are just trying to express this function by in terms of tangent at each and every point. And what is the expression of tangent? Is going to be line. So it is going to have the form y is equal to mx plus c, right? I think so. Let me just this is not y is equal to mx plus c. Let's say we use some another thing. B is equals to am plus, let's say c, where this is the new independent variable. This is the parameter. These are also parameter, and this is the new dependent variable, right? Okay, is replaced by slope, right? Let's say it is k, right? And then the new function, is given as what? Is going to be y is equal to mx plus c, right? So z, let's say that is the z. Okay, right? Now y, so it's like y is equal to, let's say, let me write this down. You may be wondering why. So y is equals to mx plus c, right? And what we need is c. C is what? C is going to be y minus mx, right? So this is what this is. It's just the this thing we have changed. Just the notation we have changed, because it is given as z. Slope has been given as z, right? So this is where z equals to new dependent variable, right? Y, what is y? Y is equals to old dependent variable, right? X is what? X is old independent variable. Remember, this is independent. So any in our earlier statement, in our this expression, this was a constant, but now we are changing the we are expressing we want to find this c. So now c becomes variable, and hence it becomes so c or z, and hence it becomes a new dependent variable, right? Y is the old, okay, this is new, this is old dependent variable, x is the old independent variable, and k now becomes the new independent variable, right? Let me highlight it. New, I use a different color. Yeah, this is the old independent variable, right? This is the old sorry, this was the red one is the old dependent variable, whereas the green one is the old independent variable, right? And this becomes the yellow new independent variable. I hope everything is clear to everyone. Yeah. So we'll move forward, right? Right. So this gives. So we have been given this. Okay. What we have been given. So it is given that y is equals to x plus 1 square, right? So now what is slope? K is what? K is nothing but slope, which is dy by dx, which is d by df of x plus 1 square, which is 2 times x plus 1 into d by dx of x plus 1. Therefore, k is going to be nothing but 2 into x plus 1 multiplied by 1. Therefore, k is 2x plus 1, right? So, z is what? Earlier we knew, right? Z is what? This is the z. Z equal to y minus kx. Z is equals to y minus kx, but y is equals to x plus 1 square and k is equals to 2 times x plus 1, and x is nothing going to be, x is going to be x only. So this is equals to x plus 1 square minus 2 times x plus 1 multiplied by x. Therefore, z is going to be x plus 1 square minus 2 times x into x plus 1. Now let us look at the option. What options we have? Oh, so options have been, so we have to simplify, right? So z is going to, what is a plus b whole square? A square plus 2ab plus b square minus 2x square plus 2x. Therefore, z is equals to what? X square plus 2x plus 1 minus 2x square minus 2x. Yeah, right? Minus 2x. So this gets cancelled, right? Minus x square, this gets cancelled, plus 1. Therefore, z becomes 1 minus x square. This is the answer. So let me write this down it in red. Sorry. Yeah. So I hope you can see my screen. Let me just check whether you guys can see my screen or not. Yeah. Yeah, I can. Yeah, I'm sharing the screen. Okay. Sorry. Uh, yeah. Yeah. So this is the answer. And therefore, z is equals to 1 minus x square. Now this is what is answer. And then what is the option? 1 minus x square. So this option D is the correct answer, right? So correct answer is option D. Okay. So I hope this question is clear to everyone. So I'll wait for a couple of minutes. If you have, you can write this down. And if you have any questions, you can ask me. I hope the concept of legendary transform is clear to everyone, and how we can use it to solve problems. Okay, so I don't see anything. So I will move on to the next question. Okay. So the next question is somewhat mathematical. Okay. So try to first understand the question as I write this down, and then try to solve it. Okay, but very, it is very important for you to first understand it. Okay, so question one, sorry, question number two. Using black, so we'll use the black one. Okay, so question two. Okay, so now what we is asked is show that x, let's say x is some property. Okay, show that, let me write it down. Show the following, let me write this down like this. Show the following is true. Okay, it is x minus x bar square bar is equals to x square bar minus x bar square. Now what is this bar? So bar is nothing but anything, let's say a bar is nothing but average of it, where a is some quantity. Or in other words, let me write this down like this. So we have average of x minus, what we have is, we have a quantity x minus average of x, right? We make it square and we take its average, and that is what we want to show. This should be equals to average of x square minus x average square. Now note that these two things are completely different quantities. They are not the same, right? These quantities, these are not the same. Okay, so it's like, let's say you have some property x. So for so what is this? This means first we we take square, we take we take square of x, and then we average out. We take, okay. So I think let me write this down like this. It's like this. Whereas this is what? This means first we take average of x, and then we take its square, right? So this is very important thing to know. It should be absolutely clear. These two things should be absolutely clear to you, right? These two are completely different properties. Okay, so now this is what is RHS, right? So now look at now let's look at LHS. Now what is LHS? So now LHS is average of x minus average of x whole square average. And in other terms, it is x minus x bar square bar. Now what does this mean? This means what we take? First, take average of x, which is nothing but average of x. Then subtract this average of x from the x value, that is original, that is the original value. Then subtract this average of x, that is from the original variable or quantity, let's say x. Now what this becomes? At this point, this becomes x minus x average. Let's say, then take the square of the above quantity. Now what is this above quantity? This quantity is x minus average of x. So now what we get is, we get x minus average of x square. Now take the average of this newly formed quantity. And what is this newly formed quantity? It is x minus x average ka square. So this is nothing but x minus average of x square and its average, right? I hope this is clear to everyone. I think I should explain this again in a very proper manner. So okay, so let us write this down. To prove, we have to prove that x minus average of x square average is equal to average of x square minus what? Minus x average square. So now first go, let us first divide our page. Okay, sorry, actually okay, so I will use different color for both of these two things. Okay, let me use blue color for LHS, which is x minus average of x square average, and then is equals to, let me use this color, x square average minus x average square. Okay, so now let us look at first of all, let us look at first part of the LHS. Okay, let us first look at RHS value. Now what is RHS? RHS, this is number one. Let us first look at the first term of RHS. First term of RHS. Okay, so now what is that? It is average of x square. What does it mean? What does this mean? So the steps are, number one, first, let's say x is some quantity. Let's say for from thermodynamics point of view, it could be temperature, pressure, like that. Then what we do? Then we take square of this quantity, and then it becomes, hence it becomes x square. And now we take the average of, let's say this, let's say we denote this x square by, let's say, a. Now we take average of a, that is average of x square, which is going to be what? Which is going to be x square. Okay, so let me, I think let me write this down also with different color so that it becomes very clear. This is what? Average square. Okay, now let us now look at the second term of RHS, right? Which is what? Which is, I think, what is that? Average square. Remember, these two terms are very different, right? So now first let's say again that x is some quantity. Now we take average of this x. We take this, take average of x. What is this? Let's say this is denoted by b. Let's say this is denoted by c is equals to, sorry, b is equals to average of x, and then take the and then take what? And then take the square of this quantity. Then it becomes what? In our denoted terms, hence it becomes b square, which is nothing but what? Average of x square. And this is what we want, right? This is what is here. This is what is here. So now let us, I hope this is clear. So these two terms are very different from each other. Square of the average of a quantity and average of a square of a quantity. Okay. So now let us look at the LHS. We'll move on to the next page. Yeah, blue one. Now let's look at the LHS. What is LHS? It looks a very complicated term. Okay, x minus average of x square, its average, right? So how do you define, right? First, let's say again, let's say x is some property, right? So then what we do? We take average of x. Now what is this going to be? And let us denote this by, let us denote this by c. Hence c becomes what? C becomes this. Okay, correct? Now what we take? We subtract this, right? Then subtract the average of x from original x value. Original values x, right? And let us denote this by, let's say, d. So then d becomes what? D becomes x minus average of x. And this is very clear. Now take the square of x, square of this newly found newly obtained quantity, that is d, right? Hence, and let us denote by this quantity by let's say E. Therefore, E becomes what? D square, which is x minus average of x square, right? So can you see we are somewhat resembling what we want. And now again there is average. So now what we do? Yeah, it's very clear. We'll take the average of this quantity. Now take the now take average of this newly found quantity, that is E, and let us denote this by F, let's say. Therefore, what becomes F becomes what? Average of E. That means average of x minus this quantity, right? Sorry. That means it is average of d square, right? That means average of x minus average of x whole square average. Right? And this is what is our LHS is. Right? So I hope this is very clear to everyone. Right? So now let us try to solve the problem. Now that the question is very clear, so it is very important for one to understand the question, then rather than directly jumping onto the problem. Okay. So now let us go and now let us try to prove it. Now let us revisit the problem and try to prove it. Right? So what was the problem? The problem was this average of x minus x average square average. This is nothing but is equals to square of average of the square of x minus average square. Okay. So now let us first look at LHS. Consider LHS. Consider LHS. So okay. So now what is LHS? LHS is average of x minus average of x whole square average, right? So this is nothing but a minus b whole square. Let us consider x as a and average of x as b. Therefore LHS is what? LHS is going to be a minus b whole square average, right? Now what is the full form of full expression of a minus b whole square? It is going to a square minus 2ab minus b square, right? Then resubstituting substituting the values of a and b, right? Therefore what it becomes? Therefore LHS becomes what? What is a? A is nothing but x, so x square minus 2 into x into average of x, right? This is a, this is b, minus average of x square, right? You see this one term from the RHS is already here, we can see it, right? This one. Now we have to simplify, right? Let me write, since a minus b square is nothing but a square minus 2ab plus b square, right? So now again LHS now transforms as, so here is bracket, this is outside, now we want to bring it inside, right? So there is one theorem. Okay, okay, write this down in the red. Theorem which tells that you have, let's say, a plus b plus c, average of a plus b. Okay, let me write this down. Average of a plus b plus c is nothing but average of a plus average of b plus average of c, right? So this is a very clear theorem. Now let's say, now how would you prove it? It's self-explanatory, right? It's very clear that this theorem is true. So for the timing, let us say that you assume this theorem, and we'll look into the proof of the theorem later. But let us first assume that this is true. Now, if this were to be true, then what is going to happen is our LHS is now going to become. So let's say this is A, this whole term is B, and this whole term is C. Then in that case, this becomes average of x square minus average of 2x into average of x minus average of x square, right? Right. Again, then we apply, this is average of x square minus 2 average of x, and then average of x minus average of x square, right? And there is again another theorem, okay, which tells that average of, so basically there are, this is theorem number 1, this is theorem number 2, which tells you that average of some quantity, let's say a, is nothing but a itself. Sorry, average of a itself. And theorem 3, it tells us that average of a into b is nothing but average of b into a, right? This is very clear, which is nothing but average of a into average of b, right? So if you apply this theorem to this above problem, if we apply theorem 2 and theorem 3 to above simplified version of LHS, then what we get? Then we get LHS as average of x square plus average of x into average of x, or let me write this down in this form, plus average of x into average of x minus 2 into average of x into average of x, right? So now one term gets cancelled here, average of x square minus average of x, therefore LHS then becomes what? This comes as it is, which is average of x square, and minus this becomes what? This becomes minus average of x whole square, and this is nothing but RHS. Right? Hence proved. Anybody has any question? So I'll give you a couple of minutes to understand it. Okay. So I hope the it is clear to everyone. If you have any doubt, you can ask. So I hope this is clear to everyone. If there are no questions, then we'll move on to the next part of the question. Sorry, next problem, the third question. Okay. Does anybody have any doubt? Yeah. So I think the question is clear to everyone. And then let us move on to the new question. The next question, that is the question three. Now, question three is about it is a very conceptual question, and it is all about a particular distribution which is majorly followed by all the natural phenomena. You take anything and any phenomena. Let's say if you go to let's say 100 random person, and then you ask them to choose a random number between 1 and 10, a one digit random number. Okay, and then when you do this many times, And when you plot the responses given by the people onto so the responses given by people on y-axis versus the possible values of x, and you take its probability. So basically probability distribution you plot. Let's say how many, let's say you are let's say 10 people out of 100 people gave took the random number as one. But if they selected a random, they chose random number one as their preferred choice, you take its probability. So probability would be what? 1 by 10. So it will be zero point 0.1. Similarly, somebody else, let's say 15 people might have said, might have picked a 2 randomly out of 10, out of one digit random number. So the probability then becomes 2 by 10, that is a zero point 0.5, a zero point 0.1. So now, when you do this step, here I said only 100 times. So if you do it infinitely many times, right, as the number of observations or the number of experiment approaches infinity, so and you plot it, you take its probability, but basically you normalize by the total number of experiments, and that is nothing but the probability. And that probability you plot onto a two-dimensional plot. So the plot which is opted is mostly the Gaussian, or which is also known as normal distribution, right? And many, almost all of this normal distribution is has been seen in many um, aspects of nature. So it's very important to have a understanding of this Gaussian curve, right? So I hope this is clear to everyone. Okay, so that is why understanding of this Gaussian curve is very important. Okay, so now I'll give the question. So there is a plot which I will give. So that plot has three different plots. So that figure basically, so I'll draw a figure. And that figure basically has three plots. Three plots for the Gaussian function, right? And one of the, and there are some variables, and you are asked to differentiate these three curves based on those variables. Okay. So let me write down the question. In figure one, three different plots for. So I'll write the question and then I'll explain. Okay. So the question is, in figure one, which I will draw, three different plots for Gaussian function are shown. Okay, one of the variables among a, b, and sigma, which will be clear from the figure, which once I draw it, is different for these three plots. Okay, and what now you want to find? The first question is the variable. Let me just put it. This is the A part of the question. The variable that is different for these three different Gaussian is what? First, they are asking that. The second question is the parameter. Okay. Oh, yeah, I didn't give you the uh, option for the first part. Okay, so the option for the first part are this is the first part. The second part of the question is this one. It concerns the value of the parameter. So in first part, you determine what is that parameter, and in second part, you just give a rough estimate as to which of that parameter is to give bigger for which plot. Okay, so it will be clear once I draw the plot. And the plot is like this. Let me use a blue color. So the plot is like this. This is 5, this is 10, this is 15, this is 20. Okay, so it starts like this. Let's say it peaks at 10 and then again it goes down. So this is plot number 1. Then let's say this plot starts like this. Okay, it goes like this. This is plot number 1. Okay, and then let me just correct this one. Okay, and the third one is like this, starts like this, goes like this, and then goes like this. Okay, this is the third one, and this is the second one. Okay? Maybe I can extend the first, and just follow me. This is one. Okay, so this is a Gaussian. These are three Gaussian part. Okay, so let me now explain the question. Okay, so what you have is, so in this figure, so this is figure number one. Okay, so now what is let us understand the question. Okay, so in figure one, which is this figure, right? This is figure one. Three different plots for Gaussian function are shown. So now what are these? So these are the three plots. So this is plot number one, this is plot number two, and this is plot number three, and these are all Gaussian functions. Now let us assume that the distribution of this, the way mathematical expression for this Gaussian function is some function, let's say f of x, and now that f of x is obviously going to depend on some parameters, right? So so although these curves, all these three curves are Gaussian and they have a same functional form. The parameters of this present inside of this function are going to determine which of these is. So it's all about the parameters. Okay, Ashwin. And one of the variables one. So these are the parameters: the a, the b, and the sigma. Right. So now, if you are aware about the Gaussian function, then you know what is this a and what is this b. And sigma is, in statistical terms, is very clear. This is the standard deviation. Right. Now, if you don't know what is this Gaussian function, don't worry, I will tell you. Okay, its function form. Okay, so what is it? One of the variables among a, b, and c is different for these three plots. Okay, so one of the parameters is different. Now, the first question which they are asking us, that the variable that is different for for these three different Gaussian is what? Okay, now if you are aware of this Gaussian function, you would know the answer to this. Okay, so and the second question is, the parameter which varies in the above case has the following descending order. So the examiner is not only asking which is that parameter, but how that parameter is varying. Right? So I'll give you a couple of minutes, 2 minutes to solve it, and then I'll give you a hint in terms of what is this Gaussian function. Okay. I think my video has gone off. I don't know why. Oh, yeah. I hope now you will be able to see my video. Okay. So just in case you are not aware, let me again tell you the question, and then I'll give you. So in this figure, this is the figure one, and three different plots are shown for Gaussian function and the variable. So this Gaussian function is depends on some variables. Though all these three has the same functional form, the parameters can determine which of them is, and those parameters are a, b, and sigma. And if you know what is the functional form of Gaussian Gaussian function, you will know what this is. Right? So I'll just give you a heads up that sigma is nothing but the standard deviation. Is different for this three plot. And the first question is, the variable that is different for these three Gaussian is what? So, and the second is, the parameter which varies in the above case has the following descending order. So the examiner is not only asking which is the different parameter, it is also asking you relatively what is the order of this parameter. Okay. So if you know what is this Gaussian function, you'll be able to answer this question. So as a heads up, I will give you what is the function form of this Gaussian function. Okay. So the function form of this Gaussian function is, I'll just give it. I'll give it in red. Hmm. function, for those of you who don't know it, functional form of Gaussian function is what? F of x equals to f of x equals to a into exponential of minus of x minus b whole square divided by 2 sigma. Right? So these are the parameters a, b, and sigma. Right? So I think you can solve based on this, and I'll give you a couple of minutes to solve it. Okay. So let me, I think, take this. Let f of x Anybody able to answer the question? Okay, so nobody can answer. So let us move on. So before, okay, so we'll just see. Now here, if you see, so actually you don't even need to know what is the functional form of this. Okay. Now, why is that? I will tell you. You don't get this part. Okay. So now you see that all of these things peak at a particular this value, right? Whereas the width of the curve changes, right? And what is this width of the curve? This is nothing but the standard deviation, right? Let us write down for all. Okay, let us see some observations. some observations from figure 1. Okay, all the three curves have maximum at some particular value of x, and this x, let us write that at this particular x, say x bar, and this x is same for all the three, right? And this is what is that x bar, let's say. The second observation is width of the curve changes. The width of the curve changes, right, with its order being following. So width of curve 3 greater than width of curve 2, which is greater than width of curve 1. What is this width of, right? Hence, we conclude that the changing parameter is somehow connected to the width of the curve, and we know that the width of the curve is somehow is not somehow, we exactly know, is correlated to standard deviation, that is sigma, right? Hence, the changing parameter is standard deviation, and we also know that the larger the width of the curve, the larger the standard deviation, larger the standard deviation. That is sigma, and therefore sigma of 3 greater than sigma 2 greater than sigma 1. Therefore, answer of part A is C, that is sigma. Answer of part B is what? C. Right? So let me again read it. So some observation from figure 1. These are the observation which we draw from this figure. Right? So from this figure, it is very clear that all the three curves, these three curves, peak at a particular point. Right? And the distance between the curve increases, right? That is the spread of the curve increases as we move from curve 1 to curve 3. And this is what I have written here. So let me read it again. Some observations from figure 1. Point number 1. All the three curves have maximum at some particular value of x, right? So all the three curves, they have maximum at a particular value of x, right? And let's call that value as x bar, or the x average, or let's say any value. And this x is same for all the three curves, right? This x is same for. So at this particular point, if I draw a line parallel to y-axis, that is going to cut all the all the three curves at the highest point. Okay. The second point is the width of the curve changes with its order. The width of the curve changes. So comma. Okay. With its order being following width of curve 3 greater than width of curve 2 greater than width of curve 1. This is very visually clear, right? So this width is greater than this width is greater than this width, right? Hence, width of curve 3 is greater than width of curve 2, which is greater than width of curve 1, right? In another words, width of curve 1 is smaller, is the smallest, and width of curve 3 is the largest, and width of curve 2 is in between the 1 and 2. Width of curve 1 and width of 1 3, sorry. Okay, and hence these are the observation and these are the conclusions. Okay, hence we conclude that the changing parameter is somehow connected to the width of the curve. It's very clear. Okay, and we know that the width of the curve is correlated to standard deviation. This is also very clear. Hence the changing parameter is sigma, right? And we also know that the larger the width of the curve, the larger is going to be the standard deviation. And hence we conclude that since the width is in this order, the standard deviation should also be in this order. That is, standard deviation of curve 3 is greater than standard deviation of curve 2, which is again greater than standard deviation of curve 1. Right? And hence the option, the changing parameter is nothing but the standard deviation, and the order of this order of this is sigma 3 greater than order of the this changing parameter, which is nothing but standard deviation, as we have shown here, is nothing but standard deviation of curve 3 greater than standard deviation of curve 2, which is again greater than standard deviation of curve 1. Right? So what are the answers? So answer here is this one, and here the answer is this one. So I hope this is very clear to everyone. If you have any doubt, you can ask. Otherwise, we'll move on to the next question. So I'll leave a couple of minutes. And also one more thing which is to be noted here is this, the same value. There is a reason, okay, deliberate reason why I have written it as average of x. This is nothing but the average of x, right? So this is what is that value we are saying. And remember that since this is same, there has to be one parameter which is same here also. So this is a hint which you can try in the next, for your thought. So we'll just take a 5 minute. So we will just take a 5 minutes of if anybody has to drink any water or anything, or they have to go washroom, they can just go. And so it is currently 8:34. We'll meet at 8:40. Okay. So 5 minutes a break. And in the meantime, if anybody has any doubt, they can ask anybody has any question. If no, then we'll move on to the next question. So we'll just wait for 3 minutes, couple of minutes for everybody else to join. Nobody has any doubt. Okay, so let us begin. So I'll write down the question. The next question is also going to be related to this some properties of this Gaussian function. Okay, so there's a proof. So what? So I will just tell you what is the ask in the question is when you take this. So this is I told this is the function form, right? So this is the function form. Now, if you take this and this is nothing but representative of this curve. Now, one interesting fact about this Gaussian curve is that when you take the area under this curve, it should all come down to 1. Why? Because this is nothing but a probability, right? It's nothing but a probability distribution. And hence, when you take this area, it's like all summation of all the probabilities should be what? It should be 1, right? So that is what the area under this curve. So area under this curve would be equal to 1. That is number 1. And the other point is other very special importance of this Gaussian functions or the normal distribution is when the sigma, right, as the standard deviation that tends to 0, the curve becomes essentially a delta function, right? Which is from graphical aspect is very clear, right? And sigma 3 we know is greater than sigma 2. So as we are going from the curve distribution 3 distribution 1, what we are observing is the sigma is getting less and less, and hence what we are saying is that the distribution is going to get narrower and narrower. What happens when this sigma becomes 0? Essentially it will become a straight line like this. It will become a straight line like this, right? So it's very clear from this graphical representation, but how do you prove theoretically? How do you theoretically or mathematically prove it? And that is what is our next question is. Okay, so I will write down the question and I will do it. I will give you 5 minutes for you guys to solve it. Okay. So now the question is question 4. Let's say part A. And this question, what you have to do is you have to prove that for Gaussian distribution, the area under the curve is equal to 1. Right? And the second part is as sigma tends to 0, the Gaussian distribution essentially becomes a delta function, right? Okay, here also to prove that. This is very clear from these plots, right? It's very clear from these plots, but how do you mathematically prove? Right? You have been given that Gaussian function, Gaussian distribution is given as f of x equals to what? 1 by sigma root 2 pi multiplied by exponential of minus 1 by 2 into z minus mu by sigma, sorry, no, sigma square. Okay, so this is what we have been given. So let us try to solve it. Okay, now let us try to solve it. Solution. part A, area under the curve equal to 0. Sorry, equal to 1. Now area is what? Area is nothing but integral from minus infinity to plus infinity, right? Therefore, area is what? Let us denote area as A. Let us denote area as this one. Area is what? Integral minus infinity to plus infinity of x dx. Right? Therefore, area is equals to, let us, okay, minus infinity plus infinity f of x. Let us put the value of f of x 1 by sigma 2 pi into exponential of minus 1 by 2. So here instead of z, because it may get confused with 2, let us put this x, half of x minus mu by sigma whole square into dx. Right? Now let us denote this integral by symbol x, sorry, I. Therefore area is equals to I is equals to integral minus infinity to plus infinity 1 by sigma root 2 pi into exponential of minus 1 by 2 x minus mu by sigma square dx. Now this sigma and 2 pi, these are the constant, right? Therefore we can take them outside the integral. And we can write this sigma root 2 pi into exponential of minus 1 by 2 x minus mu by 0 square dx, right? So let us first, so this looks like a complicated one, right? Let me highlight this. Complicated, right? So let us try to substitute this. Okay, let's do substitution. Okay, so let us do the substitution to avoid complexity. Therefore, let 1 by 2 x minus mu by sigma equals to x. Therefore, 1 by 2 x minus mu by sigma square is going to be x square, right? And also this is going to tell us what is going to be dx. So we take derivative on both the sides. Or maybe I will write this down. For dx, take derivative on both the sides. Oh, let us take it as, we'll just not take it as x. We will have to use some other variable. Let us consider this as y. Okay. Now what is dy? We need direct both sides. Therefore, 1 by 2 sigma into dx is going to be dy. Therefore, dx is going to be, yeah, 2 sigma dy, right? Right? Okay. And 1 by sorry, and what we are going to have is x square is going to be 1 by 4, sorry, 1 by 2. Okay, so not x square, this is going to be y square. Y square is 1 by 4 x minus mu by sigma square, right? So when you substitute it upon substitution of above quantities in original equation, we get I is equals to integral minus infinity to plus infinity 1 by root pi into e to the power minus y square into dy. So for I becomes what? 1 by root pi goes outside because it's a constant, minus infinity plus infinity e to the power minus y square dy. Now how are you going to solve it? Complex looking integral. How to solve it? Right? Anybody has any this on that? Any thoughts on this? So what we basically use it, we'll use the polar coordinates. But before that, okay. Okay. So now what is going to be I square? So I square. But in order to find polar coordinates, we need two integrals, right? So hence what we do is I into I is equals to I square is going to be what? It's going to be 1 by root pi into integral minus infinity plus infinity e to the power minus y square dy, okay, multiplied by 1 by root pi into integral minus infinity to plus infinity e to the power minus v square dv. Let's say dv is some variable. Say v is some variable. Therefore, what we can say is I square is going to be what? 1 by root pi multiplied by 1 by root pi multiplied by minus infinity plus infinity e to the power minus y square dy multiplied by integral minus infinity to plus infinity e to the power minus v square e to the power minus v square into dv, right? Now using polar coordinates, okay? Using polar coordinates as x equals to r cos theta and y is equals to r sin theta, okay? And the limits of the integration are minus infinity r to plus infinity and theta is going to be between 0 and 2 pi, right? Therefore, we defining the integral with successful um, substitution Therefore, I square, right? It becomes what? What is this? 1 by root pi into root pi, it becomes pi. So 1 by pi into integral 0 to 2 pi multiply, right? 0 to 2 pi into, so but prior to this, what we have is, okay, so let me just one step I skip. Prior to this, what we have is I square is going to be what? 1 by pi into integral. So this is all e to the power x, e to the power x, right? This is nothing but minus infinity plus infinity minus infinity plus infinity e to the power minus pi square e to the power minus v square dy dv. Therefore, I square is going to be 1 by pi minus infinity to plus infinity minus infinity to plus infinity e to the power minus of y square plus v square dy dv. And now this we can replace with r, right? And hence this becomes 0 to 2 pi 0 to 2 pi into e to the power minus r square into dr r dr d theta, correct? Okay? Because y square plus b square is equals to r square, and dy dv is equals to r dr d theta, right? Therefore, I square becomes what? 1 by pi into 0 to 2 pi e to the power minus r square divided by minus 2 from r is equals to 0 r is equals to infinity d theta. Therefore, I square becomes what? 1 by pi multiplied by 1 by 2 multiplied by 2 pi. Therefore, I square is 1 by 2 pi multiplied by 2 pi. Therefore, I square is 1, right? Therefore, I is equals to plus minus 1. But I is equals to area under the curve, right? And hence should be positive. Hence, discarding the negative value of I or minus 1. Therefore, I is equals to 1. Therefore, integral. Therefore, what was the question? Therefore, for Gaussian distribution, the area under the curve is equal to 1. Okay, so now let us move on to the next question. To prove as sigma tends to 0, Gaussian distribution approaches delta function. Okay, so now how will we do it? And we know that solution. Gaussian function is given by following expression. F of x is what? 1 by sigma root of 2 pi multiplied by exponential of minus half z minus mu by sigma square. Right? Now, as sigma tends to 0, 1 by 2 z minus mu by sigma whole square, this tends to infinity. Therefore, epsilon of minus 1 by 2 z minus mu by square approaches exponential of minus infinity, which is nothing but 0. Therefore, limit sigma tending to 0, 1 by sigma 2 pi into exponential of minus 1 by 2 z minus mu by sigma whole square. This approaches 0 by 0 form. Hence, we have to use what? Hence, we have to use L'Hospital rule. Hence, using Hospital's rule, we get limit sigma tending to 0, 1 by sigma 2 pi into exponential of minus 1 by half mu minus z minus mu, sorry, z or x, anything you can take, z minus mu by sigma whole square is equals to limit sigma tending to 0, right, 1 by 2 pi, or basically derivative, let's just say d by dx of exponential of minus 1 by 2 z minus mu by sigma square divided by d by dx of sigma root 2 pi. Oh, sorry, this should be not d by dx, it should be d by d sigma. Therefore, which is nothing but equal to limit sigma tending to 0, 1 by root 2 pi z minus mu square 1 by sigma cube into exponential of minus 1 by 2 z minus mu by sigma square. Therefore, which is nothing but delta function. And hence, limit delta tending to 0, 1 by sigma root 2 pi into exponential of minus 1 by 2 z minus mu by sigma square is it. Let me write this down here because this is a result. So let me write it down in a red pen. Therefore, limit sigma tending to 0, 1 by sigma root 2 pi into exponential of minus 1 by 2 z minus mu by sigma square is a delta function. Hence, this is proved. Right? So in today's class, what we have done, we have started with something called as Legendre transform. We understood Legendre transform. Okay, so let me go back. Okay, so in present class, what we did is we started with Legendre transform. We started with Legendre transform. We understood what a Legendre transform is, why it is needed, right? Why it is needed. This is what we understood, and then we solved a problem for Legendre transform. We understood this application, right? Then further we studied about Gaussian processes. No, okay. So then we studied about these various aspects which are very important. What are these mean? What is square of the mean or mean of the square or x minus? So okay. So we understood in detail, but what this each term independently means, and we also understood or emphasized that these two quantities are different. That is, taking mean of the square of a quantity is very different from taking square of the mean of a quantity, right? And then we proved this, we solved this problem, and then we showed this is true, indeed is true. Okay. Then we studied about the Gaussian, right? We studied about what are the Gaussian functions, and we tried to intuitively understand how do these Gaussian functions behave, right? Okay. These are the constant, these are the some observation and conclusions which we draw, and we showed that the width of the curve is nothing but is going to depend on the standard deviation. Okay. And then at the end we showed that the Gaussian distribution, the area under the Gaussian distribution approaches one, right? That is not approaches, it is actually exactly equal to one. And as the standard deviation approaches the value of zero, the Gaussian distribution essentially becomes a delta function, right? So I hope that this class was beneficial for you, and you are able to learn or clear some concept of it. And this class will surely contribute to for you to solve assignments in a better manner. Okay. So that's it. I think that is what I have to show for this class. Okay. So in the next class, that is in the next week, that is week 4 class, we are going to study about, the professor is going to talk about the different ensembles and how do we do the Lagrange multiplier. That is the constraint optimization using Lagrange multiplier. Okay. So in the next class, we are going to talk about it. We will solve some problems based on. So basically, we'll solve some ensembles, and we'll see how this constraint optimization under constraint by Lagrange multiplier can be helpful in many cases. Okay, we'll solve some problems, as well as we'll also solve some problems based on the Hamiltonian and the Lagrangian equations of motion. Okay. So I hope that you are able to enjoy this class, and if you have any questions you can ask, otherwise we can end this class. So I'll wait for a couple of seconds if you have any questions. Okay, so I see no questions. So I hope that you can enjoyed this class, and I hope to see you all again in the next class. Thank you. I'll be now doing the switching of the meeting. Okay.